In 1945, J. Robert Oppenheimer stood in the New Mexico desert and watched the first atomic bomb detonate, and the flash was brighter than any sun, while the shock wave flattened the observation bunker. In that moment, Oppenheimer whispered words from the Bhagavad Gita, the ancient Hindu scripture he'd taught himself Sanskrit to read in the original. "Now I am become death, the destroyer of worlds." Most people miss what really haunted Oppenheimer about that moment, and it wasn't just the destruction. The Manhattan Project had forced him and his team to engineer quantum mechanics at a scale no one had attempted before, which meant Oppenheimer saw something about the nature of matter itself, something that broke every intuition about how reality works. You think you know what an atom looks like, and you have that image in your mind right now, electrons orbiting a nucleus like tiny planets circling a sun, a miniature solar system that seems neat and comprehensible. Oppenheimer knew that picture, and he also knew it was utterly, completely wrong. The truth was far stranger than anything the human mind was built to imagine. Can you actually explain what holds an atom together? Not with words you half remember from school, but really explain it? Why doesn't the electron simply spiral into the nucleus? And why doesn't the whole thing collapse? If you pause to think about it, truly think about it, you realize that the atom, this thing you've been told is the foundation of all matter, is built on principles that defy every intuition you've ever had about how the world works. When Oppenheimer understood what's really happening inside an atom, it changed more than his physics, because it changed his philosophy. He saw why he'd been drawn to Eastern mysticism. Quantum mechanics describes a reality that Western language struggles to articulate, a reality where things don't have definite properties until observed, and where the question, what is it really, may have no answer. That realization changes everything. The trouble began, as it often does, with an experiment that gave the wrong answer. Ernest Rutherford, a New Zealand physicist working at the University of Manchester, who would later win the Nobel Prize, asked two of his students, Hans Geiger and Ernest Marsden, to fire alpha particles at a sheet of gold foil in 1909. Before this, physicists accepted J. Thomson's model of the atom as a diffuse cloud of positive charge with electrons scattered through it like raisins in a pudding, and Thomson had won his own Nobel Prize for discovering the electron, so his model carried weight. The alpha particles should pass through this cloud with barely a deflection, the way a bullet passes through fog. Most of them did exactly that, but some, a small fraction, perhaps 1 in 8,000, came bouncing back straight, as if they had struck something solid. Rutherford said it was the most incredible event of his life because the atom was not a diffuse cloud at all. There was something at its center, something incredibly small and incredibly dense, the nucleus. Here is your first mind-expanding moment, and that nucleus contains almost all the mass of the atom, yet occupies almost none of the space. Here's a scale comparison that captures it better than the usual analogies. If you removed all the empty space from every atom in every human being on Earth, all 8 billion of us, the remaining matter would fit in a volume smaller than a sugar cube. 8 billion people condensed into one sugar cube shows you how much of you is actually there. When you place your hand on a table, what you feel as resistance is not solid touching solid, but electrical repulsion across a void. You are mostly nothing, and the chair you sit in is mostly nothing, and the planet itself is mostly nothing. Oppenheimer understood this viscerally because when he designed the implosion mechanism for the plutonium bomb, he was engineering the compression of mostly empty atoms, squeezing that void until nuclei came close enough to interact. The physics of emptiness made the physics of annihilation possible. But here is where the real trouble starts. And if the atom is mostly empty space with a tiny positive nucleus at the center and negative electrons somewhere out in that vastness, why doesn't the whole structure collapse? The electrons carry a negative charge while the nucleus carries a positive charge, and opposite charges attract. According to every law of classical physics, every law Newton gave us, those electrons should spiral inward, radiating energy as they go, until they crash into the nucleus, and the process should take about 100 millionth of a second. Yet here we are, and atoms persist while matter stays stable. Something prevents the catastrophe. That something is the central revolution of 20th century physics, and it requires us to abandon almost everything we thought we knew about how objects behave. Oppenheimer called it the greatest collective intellectual achievement in human history, and he wasn't exaggerating. The resolution came from a place most physicists did not expect to look: from the study of light. Max Planck discovered something revolutionary in 1900 while trying to solve a technical problem about how hot objects glow. and he found that light is not continuous but comes in discrete packets, which he called quanta. Planck won the Nobel Prize in 1918 for this discovery, though he initially considered it a mathematical trick rather than a statement about reality. A few years later, Albert Einstein extended this idea, showing that light itself behaves as if it were made of particles, photons, even though it also behaves as a wave, and this insight from his miraculous year of 1905 earned Einstein his own Nobel Prize in 1921. This was the first great crack in the classical picture, because nature, at its smallest scales, does not flow smoothly, it jumps. Niels Bohr, a Danish physicist who would become one of Oppenheimer's most important mentors, took this insight and applied it to the atom, and his proposal was radical. Electrons, he said, cannot orbit the nucleus at just any distance, but are confined to specific orbits, specific energy levels. An electron in one of these levels does not radiate energy, but simply stays there, stable, until something causes it to jump to another level. When it jumps down, it releases a photon, and when it absorbs a photon, it jumps up. But between the levels, there is nothing. The electron does not spiral gradually, but leaps instantaneously from one state to another. Bohr won the Nobel Prize in 1922 because his model explained the spectral lines of hydrogen with stunning precision. Think about what it implies, though. There is no trajectory and no path the electron takes between one orbit and another. The electron is simply here, and then it is there, and the question of what happened in between has no answer. This isn't merely that we cannot observe the transition. The transition, in any classical sense, does not exist. This should unsettle you because it unsettled Einstein so deeply that he spent the rest of his life trying to prove it wrong. Oppenheimer felt unsettled too, but differently, and he saw in this strangeness a resonance with ideas he'd encountered in the Bhagavad Gita. The Hindu concept of Maya, the idea that perceived reality is illusion, that the world of separate objects is not ultimately real, suddenly seemed less like mysticism and more like physics. Bohr's model, revolutionary as it was, remained a kind of patchwork that explained the hydrogen atom beautifully, but struggled with anything more complex. The deeper truth required a more complete reconstruction of physics itself, a reconstruction carried out in the 1920s by Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Born, and others. What emerged was quantum mechanics, later organized into what we now call the standard model of particle physics through 4 Nobel Prizes and a complete reimagining of reality. Quantum mechanics does not merely refine our picture of the atom, but replaces it with something entirely different. Here is the heart of it. An electron does not have a position in the way a billiard ball has a position. Until you measure it, the electron exists in what we call a superposition, a simultaneous occupation of many possible states. The electron is not hiding in one place with its location unknown to us, but genuinely does not have a definite location, and the uncertainty is not a limitation of our instruments, but a feature of reality itself. Heisenberg formalized this in his uncertainty principle, the work that earned him the 1932 Nobel Prize. And you cannot know both the position and the momentum of a particle with arbitrary precision. The more precisely you determine one, the less precisely you can determine the other. And this is not a statement about measurement error, but a statement about nature. An electron cannot possess both a definite position and a definite momentum, because the properties themselves are not fully defined until observation forces a choice. Let me make this concrete by asking, where is the electron right now? Quantum mechanics answers with a probability distribution, a cloud of likelihood spread through space, where in some regions you are more likely to find the electron if you look, and in other regions less likely. Until you look, the electron is not in any particular place within that cloud, but is distributed across all of them. Richard Feynman, who would later work under Oppenheimer at Los Alamos and go on to win his own Nobel Prize, put it memorably when he said that anyone who claims to understand quantum mechanics doesn't understand quantum mechanics. Feynman also developed tools to work with it, and his famous diagrams, those deceptively simple stick-figure drawings of particles dancing in and out of existence, gave physicists a way to calculate without necessarily comprehending. This is what replaced Bohr's orbits, and we no longer speak of electrons circling the nucleus in tidy paths, but speak of orbitals, three-dimensional probability distributions, standing waves of likelihood that surround the nucleus in shapes of extraordinary beauty. Some are spherical, while others have lobes or rings or complex nodal patterns where the probability of finding the electron drops to 0. Orbitals are standing waves, exactly like the harmonics on a guitar string, and the atom, in a sense, is an instrument playing itself, vibrating in quantum modes that determine everything about how it interacts with light and other atoms. Consider the simplest atom, hydrogen. One proton, one electron, and the ground state orbital is a sphere of probability centered on the nucleus, densest near the center and fading gradually outward. There is no edge and no boundary where the electron definitely is not, and the probability simply becomes vanishingly small. In principle, there is some finite chance of finding the electron anywhere in the universe, but in practice, it is almost certainly within a few billionths of a meter of the nucleus, though not at any particular point within that region. What happens when you add energy? The electron can transition to higher orbitals, excited states with different shapes, different probability distributions, different nodes where the likelihood drops to zero. These are not different paths around the nucleus, but different modes of existence, different ways the electron field can vibrate around the central charge. And this is why the electron does not collapse into the nucleus, because a classical particle, attracted by the positive charge, would indeed spiral inward. An electron is not a classical particle, but a quantum object, and the mathematics of quantum mechanics specifically, the Schrödinger equation produces solutions in which the electron's probability distribution does not collapse. The electron cannot exist entirely at the nucleus, because that would violate the uncertainty principle, and to confine it to such a tiny space would require an infinite uncertainty in its momentum, which would immediately spread it out again. The atom is stable, not despite quantum mechanics, but because of it. Stop and think about that, because the reason you exist, the reason any matter exists in stable form, is that the classical picture of reality is wrong. If electrons behaved as Newton's laws suggested, there would be no atoms, no molecules, no chemistry, no biology, no you. We exist because the universe runs on quantum rules, and in a classical universe there would be no observers to notice its absence. Oppenheimer grasped this with unusual depth because at Los Alamos he was engineering devices that depended on quantum mechanics being exactly right, not approximately right, not philosophically interesting, but precisely correct in ways that determined whether bombs would fizzle or detonate. The abstract became terrifyingly concrete. Let me take you inside the nucleus itself, where the strangeness deepens. The nucleus contains protons and neutrons, collectively called nucleons, and protons carry positive charge, while neutrons carry no charge at all. Here is the puzzle. Positive charges repel each other, and the protons in a nucleus are packed together at distances far smaller than an atom. The electromagnetic force trying to push them apart is enormous. So what holds them together? The answer is a force far stronger than electromagnetism, appropriately called the strong force, one of the four fundamental forces of nature alongside electromagnetism, the weak force, and gravity. The strong force operates only at extremely short ranges, shorter than the size of a nucleon, but within that range it overwhelms the electrical repulsion and binds protons to protons, protons to neutrons, neutrons to neutrons, holding the nucleus together against the electromagnetic force that would otherwise tear it apart. But here is the beautiful part. The strong force, at the level of protons and neutrons, is actually a residual effect of something deeper. Protons and neutrons are not themselves fundamental, but are made of quarks, particles that Murray Gell-Mann predicted in 1964 and gave their whimsical name, drawn from a line in James Joyce's Finnegan's Wake. Quarks are bound together by the exchange of particles called gluons, and the theory that describes this binding is called quantum chromodynamics, one of the great achievements of 20th century physics. Gell-Mann won the Nobel Prize in 1969. Quarks possess a property called color charge, not color in any literal sense, but a quantum number that plays a role analogous to electric charge in electromagnetism, and there are three color charges: red, green, and blue. Gluons carry color charge themselves, which makes the strong force behave in ways utterly unlike any force you've encountered, because as quarks move apart, the force between them does not weaken but strengthens. You cannot isolate a single quark, and the energy required to pull two quarks apart becomes so great that it creates new quarks from the vacuum itself, which is called confinement. Think about what that means. Every atom in your body contains quarks that have never existed in isolation since the first moments after the Big Bang. They are always bound, always together, connected by the strongest force in nature, and quarks are the only fundamental particles that cannot exist alone. Pull them apart, and the universe creates new partners for them rather than allow solitude. Some physicists joke that quarks are particles with attachment issues, and here is where it gets even stranger. Quantum mechanics tells us that particles are not merely points of matter, but are excitations of underlying fields that pervade all of space. The electron is not a little ball orbiting the nucleus, but is a ripple in the electron field, and the photon is a ripple in the electromagnetic field, while the quarks and gluons inside protons and neutrons are ripples in their respective fields. Feynman's diagrams were maps of these ripples interacting. This perspective, quantum field theory, reveals something extraordinary about the inside of an atom, because even in what we call empty space, the fields are never truly quiet. They fluctuate constantly, creating and annihilating pairs of particles and antiparticles in a ceaseless quantum foam. And these fluctuations are not merely theoretical abstractions, but have measurable effects. The Lamb shift, a tiny deviation in the energy levels of hydrogen, measured in 1947, was one of the first experimental confirmations of this quantum turbulence, and Willis Lamb won the Nobel Prize for that measurement. What does this mean for your picture of the atom? The vacuum itself is not empty, but seethes with potential, and between the electron orbitals and the nucleus, in all that apparent void, there is activity, virtual photons mediating the electromagnetic attraction, virtual electron-positron pairs winking in and out of existence. The emptiness is full. Inside the nucleus, these fluctuations are even more dramatic because the proton is not simply three quarks sitting quietly together. The proton is three quarks embedded in a roiling sea of virtual gluons and virtual quark-antiquark pairs, all appearing and disappearing faster than any experiment can directly observe. When we measure the mass of a proton, 938 million electron volts, only about 9 million electron volts comes from the masses of the three quarks themselves. And the rest, over 98%, comes from the energy of this internal chaos, converted to mass through Einstein's equivalence. Let me say that again. The mass of ordinary matter, your mass, does not primarily come from the masses of the particles that compose it, but comes from the energy of the strong force binding those particles together. E equals mc squared works in both directions, so mass becomes energy in nuclear explosions, while energy becomes mass inside every atom. This is why particle physicists sometimes wince at diet culture language about burning calories, because you're not burning anything. You're converting mass to energy at the atomic level, the same process that powers the sun, and every metabolism is nuclear physics in slow motion. Oppenheimer understood this equivalence with terrible clarity, because the bomb he built converted less than a gram of matter into energy, and that was enough to flatten a city. The binding energy inside atoms, the energy that gives them most of their mass, is the energy that ended the Second World War. I want to return now to a deeper question, a question that troubled Bohr and Einstein and Oppenheimer and everyone who thought seriously about what quantum mechanics was telling us. When we measure an electron's position and find it at a specific location, what happened to all the other possibilities? The wave function, that mathematical object encoding the probabilities, appears to collapse instantaneously, and the electron that was spread across many possible positions is suddenly here and only here. How does that happen, and what does it mean? There is no consensus on this. Bohr and his colleagues in Copenhagen argued that the question itself is misguided, that quantum mechanics tells us what we will observe, not what is really happening when we are not observing, and the wave function is a tool for prediction, not a description of reality. Oppenheimer largely accepted this view because it resonated with his reading of Eastern philosophy. Perhaps the question, what is it really, assumes a kind of underlying reality that doesn't exist. Other interpretations disagree. And in 1957, Hugh Everett, then a graduate student working under John Wheeler, proposed that all possibilities continue to exist, branching into parallel worlds with every quantum measurement. Wheeler supported the idea privately, but worried about Everett's career because the physics community was not ready, and Everett eventually left physics for defense research, frustrated by the reception. His interpretation gained followers only decades later. Still others, like David Bohm, proposed hidden variables beneath the quantum description, a deterministic reality underlying the probabilistic appearance, and Einstein hoped something like this would be true. The universe, he felt, should not play dice. This debate isn't merely philosophical anymore, because in 2020 a team in Vienna performed what's called a Wigner's friend experiment, a scenario dreamed up decades ago but only recently made testable. The results challenged all existing interpretations simultaneously. And we may need new physics just to explain what observation means. What I want you to understand is that these are not merely technical disputes, but go to the heart of what science can tell us about the nature of reality. For centuries, physicists assumed that their equations described an objective world that exists whether we look at it or not. And quantum mechanics suggests something more troubling, that observation and reality are entangled in ways we do not fully comprehend. The atom is not simply a small thing, but is a window onto a different kind of existence, one where the categories we use for the everyday world, position, trajectory, definite state, lose their meaning. Oppenheimer saw this window and saw that physics had arrived at the edge of what Western philosophy could articulate. He turned to the Bhagavad Gita, not as escape from physics, but as complement to it. And the Gita's teaching that the world of separate objects is Maya illusion seemed to him less mystical after quantum mechanics than before. If electrons don't have definite positions until observed, if atoms are mostly emptiness, if matter is really energy in another form, then perhaps the solid world we perceive is exactly what the ancient texts described, a veil over something stranger and more fundamental. This isn't just physics trivia, because every quantum computer being built right now by Google, IBM, IonQ, and dozens of startups is an attempt to engineer these probability clouds. Qubits exist in superposition, just like electrons, and quantum computing is literally applied atomic weirdness. The same uncertainty that prevents electrons from collapsing might soon break every encryption system on Earth, and also revolutionize drug discovery, climate modeling, and artificial intelligence. Oppenheimer worried about what physics could destroy, and we now grapple with what it might create. Most people never really ask why the periodic table has the structure it does, or why there are noble gases that barely react with anything, why metals conduct electricity, why atoms bond in some configurations but not others. The answers all trace back to quantum mechanics, to the shapes of electron orbitals, to the Pauli exclusion principle that forbids two electrons from occupying the same quantum state, to the way orbitals fill in sequence as you add electrons to heavier and heavier atoms. Wolfgang Pauli won the Nobel Prize in 1945, the same year as Trinity, for the exclusion principle, and it explains why matter takes up space at all. Chemistry, all of chemistry, is applied quantum mechanics, and the molecules that make up your body, the reactions that sustain your metabolism, the bonds that hold DNA in its double helix, all emerge from quantum rules governing how electrons arrange themselves around nuclei. When you understand this, you see the world differently, because a leaf absorbing sunlight is an exercise in quantum electrodynamics. The smell of coffee is a consequence of molecular shapes determined by orbital geometries, specific three-dimensional probability clouds locking into receptors in your nose, and the fire burning in a hearth is electron transitions, photons released as atoms reconfigure. There is a hidden quantum poem beneath every familiar experience. Every time you touch something, you are experiencing the Pauli exclusion principle in action, because your hand does not pass through the table, since the electrons in your skin cannot occupy the same quantum states as the electrons in the wood. They push back. Not through direct contact, there is no contact at the atomic level, only fields interacting across emptiness, but through the quantum mechanical prohibition against identical particles sharing identical states. Solidity itself is a quantum phenomenon. Every time you see color, you witness electron transitions, and the blue of the sky, the red of a sunset, the green of a leaf, each is a story of photons absorbed and emitted as electrons jump between energy levels. Light and matter are dancing together in a choreography written by quantum rules. What then is really inside an atom? Not a miniature solar system, and not little balls circling bigger balls. Inside an atom is a nuclear core bound by the strongest force in nature, itself composed of quarks and gluons in perpetual quantum flux energy masquerading as mass. Around that core, there are no orbits but only probability clouds, standing waves of electron presence that do not exist in definite locations until measured. Between the nucleus and those electron clouds lies mostly nothing, an emptiness that somehow constitutes the solid world, seething with virtual particles appearing and vanishing in the quantum foam. The atom is stable because classical physics is incomplete and holds together because of quantum rules that forbid collapse. Its very mass arises mostly from energy, not substance, and at the center of it all lies an irreducible strangeness. The particles that compose matter do not have definite properties until something forces a choice. This is what Oppenheimer saw that others missed. Perhaps not a new particle or a clever experiment, but the full weight of what quantum mechanics implies. He saw that physics had outgrown the comfortable assumption that reality exists independently of observation, and saw that the atom teaches us nature, at its roots, operates according to principles that language can only gesture toward. We build our equations and make our predictions, and they work with extraordinary precision, but the question of what the equations describe, what reality looks like when no one is measuring, remains open. That is not a failure of physics, but is physics maturing enough to recognize its own boundaries? Oppenheimer spent his later years thinking about these boundaries because after the war, after Los Alamos, after the security hearings that stripped his clearance and broke his public career, he returned to teaching and philosophy. He lectured on the relationship between science and culture, on the limits of knowledge, on the responsibility that comes with understanding, and he had seen inside the atom and built weapons from what he found. He had also seen that the atom reveals a universe stranger than weapons or wonder, a universe where the deepest questions may not have answers in any language we know. What's really inside an atom? Ultimately, a mystery we have learned to calculate but never fully to explain, and that, I think, is not a reason for frustration but a reason for wonder. The universe is under no obligation to make sense to us, and that it makes as much sense as it does that we can peer inside the atom and find comprehensible structure, that the equations work, that the bombs detonate, and the computers compute, and the chemistry unfolds according to quantum rules, is already more than we had any right to expect. Oppenheimer knew this, and in his later years he quoted the Gita less about destruction and more about wisdom. These bodies are known to have an end. The dweller in the body is eternal. He had seen inside the atom and discovered that matter itself is not what it appears, and perhaps that was consolation. Perhaps it was just more mystery. Either way, he saw what others didn't, and now, so do you.